Next up, we have Danny Lange. Danny is the Senior Vice President of Artificial Intelligence and Machine Learning at Unity Technologies. In his role, he leads the company's innovation around AI and machine learning while focusing on bringing AI to simulation and gaming. Prior to joining Unity, Danny was the head of machine learning at Uber, where he led efforts to build the world's most versatile machine learning platform to support the company's hyper growth. He also served as general manager of Amazon Machine Learning, an AWS product that offers machine learning as a cloud service. Before that, he was principal development manager at Microsoft, where he led a product-focused team on large-scale machine learning for big data. Please join me in welcoming Danny to the stage.
Thank you very much. I'm happy to be here. Simulation and synthetic data, that's generated data, is a game changer for AI. And that's what I'm going to talk about today. But first, allow me to introduce Unity and the Unity engine, which is driving this change. Unity Technologies offers an engine. We call it a real-time 3D platform. It's used for games, AR, VR, film, automotive, robotics. It's about 60% of all games are made with Unity. It's installed on over 6 billion unique devices, and over 3 billion monthly active players play a game developed on the Unity platform. Yeah. And we got over 5,000 employees working across the world with the headquarters in San Francisco. And our vision for AI using the Unity engine is to enable organizations of all sizes to create, deploy, and unlock the value of AI in computer vision, robotics, and spatial simulation. That's like 3D simulation. So you may ask, what does a game engine has to offer? What does it have to offer for AI and for development of AI? Well, games have been used to drive AI research for a very long time. Over 70 years ago, Claude Shannon published the first paper on programming a computer for playing chess. We have seen checkers being used in '89. When I was at IBM, there was IBM Deep Blue, who defeated Garry Kasparov in chess. And IBM Watson defeated its competitors in Jeopardy using natural language processing. And more recently, we have seen DeepMind's AlphaGo defeat the world champion in Go. And more recently, we have also seen a number of efforts using video games to progress AI. So we have seen DeepMind, OpenAI, Microsoft developing various kinds of AIs for playing video games. Yeah. So video games are fantastic to drive AI. So what is it with video games that's so interesting? Well, there are 4 dimensions to AI. There's the visual component. So video games offer that. We all played games. They are very rich in graphical expression. There's also the physical component, that video games have gravity, collisions, inertia, all of the physical components from the real world. And then video games also have cognitive elements. You have to solve puzzles of various kinds in games. It can be word games, but it can also be like games where you have to collect and solve problems to get to the next level. And finally, video games also have the social aspect. Yeah. So all these 4 dimensions are also relevant to progress AI and to be used for the advancement of AI. So look at our real-time 3D engine. It's a spatial 3D environment with 3D assets. It's a graphical rendering system with advanced lighting. And it's multisensory in the sense that you can put cameras in various places in games to basically get different point of views. And finally, there's the physics engine. We're using Physics 4.1 from NVIDIA that gives you the physical reality. So in many ways, you have your private AI biodome with a game engine like the Unity engine. So let's talk about simulation, and in particular for autonomous systems. So the anatomy of autonomy is really on one side perception, so it's the computer vision aspect with sensors and the ability to have cameras and different types of cameras in the environment. It's building machine learning models that do object detection. And then there's a control aspect. So you have an autonomous system, it can perceive the world around it, but you also need to control itself within that world. There are many ways to implement control in autonomous systems. I'm going to focus today on reinforcement learning, which is essentially nature's method of learning. So when we talk about perception, that's computer vision. It's very complex actually in the real world to do this. You go and collect real world data at a high cost and you manually label that data to train your machine learning system, yeah? Or you try to have a robotic arm solve a task and it moves at the speed of the physical world, yeah? You have complexities arising from multiple technologies being involved. And you have basically the challenges of machine learning training itself. You have privacy, safety, and regulatory compliance hurdles. I mean, like go and take pictures of people and violate their privacy and use that in your machine learning model. It's all trouble. And then, of course, you have the challenge of doing all this at scale. You need immense amounts of data to train your machine learning systems, yeah? So this is synthetic data advantage. If you can generate all that data, you have high volume at a very low cost. You can generate at high speed, and you have elasticity, meaning that you can generate the data you need. If you need more, you generate more, and if you have enough, you stop. Yeah, and you only pay for the resources consumed when you generate your data. You can analyze your data, and you have a fundamental level of ease of use. So here's an example of a computer vision training data set. You have bounding boxes, 2D, 3D bounding boxes. You have instance and semantic segmentation. All of that is generated and fed into a training system. You have randomization of the environments. You can change the materials, the colors, and you can basically change the lighting. Yeah. So imagine that in a particular scene, you have thousands and thousands of combinations you can cheaply generate to train your computer vision model. And this can be in a warehouse situation, it can be retail, or it can be a city view. Here's an example of a autonomous vehicle simulator. You see cameras, you see depth cameras, you see an example of LiDAR here. So it's a variety of multimodal sensors. Let's jump from computer vision to control using reinforcement learning. This is the tasks we want to solve. We want to have robots doing very complex tasks, yeah. And reinforcement learning is basically nature's method of doing this. It's a thing about observing, taking action, and reap the rewards or the penalties. So it's a feedback loop. It's the AI feedback loop. And essentially a system, a learning system, goes from exploring to exploiting. And let me give an example of that, a very simple example, just so that we all get on the same page here. At Unity, we developed a small game to be played by a computer. It's basically observing pixels. A computer is able to take actions, and it wants the yellow chicken to cross the road, yeah? And there's a reward signal, which is negative, being hit by a car, and it's positive for gift pickup. And if you look at this video, it's training from scratch. It has no idea what's going on. It's completely random movements. You see it's moving more backwards than forwards. But in a moment up on the right, it will accidentally collect a gift package right there and then be hit by a car. So in a few seconds, it learns 2 bits of information, yeah? After some training, it actually gets pretty good at it. You see it collects packages, gets hit by cars, but overall, it's going pretty well. It will show some behavior where it stops, try to avoid vehicles, These vehicles are coming in completely randomly, so it's never seen any particular episode before. But then look, after 6 hours of training, it has become superhuman. Yeah. So by going through this feedback loop of observing, acting, and reaping the rewards, it has become perfect at crossing the road. Let's see if we can use this for some other purposes. In this case, two agents are playing some sort of tennis, learning from scratch to do that. Or you have agents, 4 agents playing against another 4 agents in some kind of indoor soccer game, learning that from scratch as well. And look at the gaming. The play here is not as random as it looks. Actually, from scratch, the system has learned that having a goalie is a really great idea. So you can see that even we call that emergent behavior. So that very complex behavior can come out of absolutely nothing just through millions and millions of plays. Yeah, and that is also relevant when you start talking about autonomous systems. Here, we are training a robotic arm to learn to touch an object no matter where it's situated. Yeah, so it basically uses reinforcement learning to be really good at figuring out how to touch an object at a random location. In Unity, we have some packages. In this example here, it allows us to import a robot into Unity. Robot manufacturers, they specify their robots in a formal format called URDF. And we can basically import those robots directly into Unity. And now you have essentially a digital twin of that robot. And now you can train that robot. You can train it to move objects. And in this example here on the left, you see a simulated robot moving an object. And then on the right side, you see actually a physical robot using the same piece of software to move an object. Yeah? And that's the whole idea here, is that you use Unity as a very low cost and very efficient and very scalable way of simulating a real world robot. Yeah? You can imagine how long time these actions would take if you try to work with a real physical robot. Yeah? It's much easier and much faster to make changes and make mistakes. You don't break anything and so on. So having talked about perception or computer vision and about control through reinforcement learning, and remember there are many other ways you can actually hard code the robot as well. It doesn't have to be in reinforcement learning. At the fundamental level, it's all about the data here. Yeah, I have seen an exponential growth of data. We can call it Moore's law of data in AI. It seems that the amount of training data doubles every 18 months. And the world is running out of real world data. We need synthetic data to keep it up. And if you think about it, a game runs at 30 to 60 frames per second. That's the FPS, yeah? So it's basically 30 to 60 images per second, yeah? In simulations, you can feed a computer an unlimited number of frames per second. You're not limited to the human perception and the eye and the brain here, yeah? And to put that in perspective, 1 year of your life at 30 frames per second is about 1 billion frames. So 1 billion frames is a year of your life, yeah? Well, I can run that in servers at increased frame rate. I don't have to run at 60. I can run 120, I can maybe run 200, I can maybe run 500, it depends on the hardware, the software. I can also run on a wide range of instances in a cloud service. Yes, I can have massive parallelism. Yeah, and I can actually also have active learning, which is I can have a training feedback loop where my data is being customized to the training situation. Yeah, so look at this as using simulation to really unlock data generation for AI. Here's an example. It's from OpenAI. They use Unity to simulate a robotic hand flipping a cube. Yeah, and in this particular example, OpenAI generated 300 billion simulated frames. So with 1 billion frames representing a year of your life. 300 billion frames are basically 300 years of experience. So you use 300 years, or what's equivalent to 300 years of experience, to train a machine learning model to create a loop here between the camera, the machine learning model that controls the physical robotic hand. Yeah. So again, it's like the example I showed with the robotic arm. We're going from the virtual, from the simulation to the physical robot. Now, let's take this a step further. So in this case here, it's again OpenAI using Unity to train a robotic hand to solve Rubik's Cube. You can see this is a much, much harder problem. If you ever tried it yourself, it's actually really difficult to do this one-handed. Yeah. In this case, OpenAI used 10 trillion simulated frames. So that's 10,000 years of experience, of virtual experience, going into training the machine learning model doing this highly complex task. Yeah. So you can see how we went from 300 billion to 10 trillion to solve more complex tasks. Yeah. Look at the complexities of a self-driving vehicle. You have to drive down the street, simulate a drive down the street in different lighting and weather conditions. And you have to prepare the vehicle, train the vehicle for a wide range of situations. Yeah? And what I'm showing in this video is the idea that you do this at extreme parallelism to basically create all these different situations, all the different modalities from camera. You see cameras in there, you see segmentation in there, you see depth cameras, there's LiDAR as well. So you basically do that at very, very large scale to provide the necessary training data for the autonomous system. Fortunately, all of this is available to you. For the developers, the things I've shown you today is all open source. We have the Unity Perception package on GitHub. It's basically a package that allows you to generate visual training data for computer vision purposes on your laptop. We also have the Unity Robotics package. It supports URDF for importing robots. It also supports ROS, the robot operating system. It's a standard for interacting with robots. So you can actually don't have to use reinforcement learning. You can use traditional programming up against the ROS API. So Unity will support ROS natively to simulate your robot. Actually, it's fantastic for testing your robot dynamics before putting it on a physical robot. And the third package is the ML Agents package. I think it's the most popular reinforcement learning framework in the world. It has tens of thousands of users using it to advance reinforcement learning, to create characters in games based on reinforcement learning rather than sort of old-fashioned coding. Yeah. So all three packages available on GitHub, is all for free. You can just go and play with it. There's more information on the business side. We have a lot of information about Unity Computer Vision, and we also have a Unity Robotic Simulation and cloud-based service. And finally, for those who are very technical, I want to have a peek under the hood. Of course, you can go to the GitHub archives and look at source code, but we also have two publications. One is Unity Perception, generates synthetic data for computer vision. You can go and fetch that on the internet. And the other one is for ML Agents. It's Unity, a general platform for intelligent agents. Both papers are academic in nature and explains in more detail how these things work. And that was all I had in store for you today. I hope you enjoyed it. I encourage you to go and try it out. Feel free to follow me on Twitter or LinkedIn, and I hope you enjoyed it. Thank you very much.
What a great session. Thank you, Danny.